Have you ever paused to wonder what truly makes those incredibly powerful AI models we interact with every single day? From the smart features on your phone to the massive cloud services behind the scenes actually run efficiently in the real world.
Sure.
They're everywhere, yeah. But under the hood, there's a surprising challenge lurking. We call the AI efficiency gap. Think about it. Deep learning models, especially the cutting-edge ones like, say, the GPT series, are mind-bogglingly powerful, billions, even trillions of parameters. But that sheer size, that computational hunger, it creates this massive deployment wall. And this wall stops many applications cold, right? Whether you're trying to get advanced AI onto a tiny edge device or even scaling it in the cloud. We often see expensive GPU clusters significantly underutilized, sometimes running at like a dismal 35–45% efficiency.
That's right. It's shockingly low sometimes.
And this gap isn't just about sluggish performance, you see. It translates directly into sky-high operational cost and, well, a significantly larger carbon footprint. It's a real bottleneck.
And what's truly fascinating here, I think, is that bridging this gap isn't just a technical hurdle anymore. It's rapidly becoming the defining measure of AI leadership.
Really? How so?
Well, the competitive advantage in AI is shifting. It's no longer just about achieving the highest benchmark score in a lab, It's about the ability to deploy and integrate these powerful AI systems at scale, practically and economically across your entire operation. That's where the real value is unlocked now.
And that, dear listener, is precisely what this deep dive is all about. Model compression. We're going to unpack this absolutely essential suite of techniques that allows us to take these powerful, yet kind of unwieldy models and make them practical, scalable, and economically viable, all while minimizing that crucial accuracy loss.
Exactly. Minimizing the hit to accuracy is key.
For this deep dive, we've pulled deep insights from Deep Learning Model Compression Explained and the Developer's Handbook to Advanced Model Compression. So our mission today is to break down the core pillars of model compression, show you how they actually work, and then reveal how they're combined to make AI truly efficient for you.
Okay, let's unpack this then. When we talk about shrinking these massive AI brains and making them run faster, there are, 4 primary ways we do this?
That's right. 4 main pillars, as we like to call them. First up is quantization.
Quantization, okay.
Imagine taking a highly detailed photograph, like a 32-bit floating point image, and simplifying it, maybe down to an 8-bit version. You still recognize everything, right? But the file size is much smaller and quicker to process.
Ah, okay.
That's essentially what quantization does for the numbers inside a model. It reduces their numerical precision to shrink the model size and speed up computation.
Got it. Makes sense. What's next?
Then there's pruning. Think of it like a skilled gardener trimming a bush.
You identify and remove redundant or unimportant branches. These could be individual parameters or even entire structural components from the network. You're effectively trimming the fat without losing the plant's essential shape or health.
Trimming the fat. I like that. Okay, pillar number 3.
Our third pillar is knowledge distillation, often just called KD.
KD, right.
This is where you have a brilliant, experienced teacher model, maybe a massive, slow, but highly accurate one.
Okay.
You then train a smaller, more efficient student model. But here's the key. The student learns directly from the teacher's nuanced responses, not just the basic right-wrong answers.
So it learns the subtleties.
Exactly. It's like a prodigy learning from a master, picking up all the implicit knowledge.
Interesting. And the last one.
And finally, low-rank factorization, or LRF.
LRF.
This is a bit more mathematical, but think of simplifying a complex musical chord. Instead of hitting all 10 notes, maybe you find 2 or 3 core notes that still convey the same harmony.
Okay, a simpler representation.
Precisely. LRF approximates large, complex weight matrices in a neural network with 2 or more smaller ones by exploiting their intrinsic mathematical structure, their low rank.
So if you're building AI systems, you can really see how mastering these tools, it's not just a niche skill anymore, is it?
Not at all. It's rapidly becoming a core competency for anyone who needs to take AI from like a cool experiment in a lab to a real-world product that actually works efficiently.
Yeah, makes total sense. Now, let's say you've spent weeks, maybe months, training your amazing AI model. You used, I don't know, PyTorch or TensorFlow. The next hurdle is getting it to run smoothly and consistently on vastly different hardware, right? Maybe a cloud GPU, some obscure edge device, or even your phone.
The deployment challenge.
Exactly. And without rewriting everything from scratch, this is where ONNX comes in, the Open Neural Network Exchange.
Spot on. ONNX swoops in like a universal translator for models. It completely decouples your training environment from your deployment environment. It's a bridge.
The universal translator. I like that analogy. So how does it work technically?
Well, an ONNX model, at its heart, is essentially a serialized computation graph. Think of it as a universal blueprint for your model's operations. It's a language any compatible runtime can understand. It's defined using protocol buffers, and if you were to peek inside...
If I dared to peek inside.
Yeah, you'd find key parts. The model proto, which is like the cover sheet with all the model's metadata. Then the graph proto, detailing the actual computational logic. It's a directed acyclic graph showing how data flows.
Okay, the flow.
Then node proto for each individual operation, like a convolution or matrix multiplication. And finally, tensor proto and value info proto define the data itself, including your all-important trained weights and biases, which are called initializers.
That sounds incredibly versatile.
Yeah.
But, a blueprint isn't useful unless you have someone who can read it and build from it, right?
Exactly. And that's where ONNX Runtime, or ORT, comes in. This isn't just a concept. It's the high-performance inference engine that actually executes these ONNX models.
High performance, you say?
Oh, yeah. When I say high performance, I mean it powers massive services like Microsoft's Bing and Office products. So it's definitely built for serious scale and enterprise-level reliability.
Wow, okay. So it's battle-tested.
Yeah.
What gives ORT its power?
It's got a few key advantages developers absolutely love. First, it's execution providers, or EPs.
EPs, okay.
Think of these as specialized hardware acceleration teams. ORT detects available hardware, say, an NVIDIA GPU. Then the CUA, or TensorRT, runs portions of your graph on that specific hardware for maximum performance.
Ah, so it automatically uses the best hardware available.
Precisely. And if an EP can't handle a specific operation for some reason, ORT seamlessly falls back to the CPU.
Yeah.
Your model always runs.
That's smart. No code changes needed.
None. You get the best possible performance on whatever hardware is available without changing a single line of your model code. It's pretty elegant.
Nice. What else?
Secondly, ORT boasts impressive cross-platform and language support. Linux, Windows, iOS, Android, Python, C++, C#, Java, even JavaScript. That flexibility is a huge deal. And thirdly, ORT has robust built-in graph optimizations. These automatically transform your model graph for better performance.
Like what kind of transformations?
Things like constant folding, pre-calculating parts of the graph that don't change, or eliminating redundant operations. But the real kicker, performance-wise, often comes from node fusions.
Node fusions.
Yeah, combining multiple simple operations, like maybe a convolution followed by adding a bias, into a single, much more efficient fused operation that runs faster on the hardware. These can be applied online when the model loads, or offline to save an already optimized version.
Okay, so what does this all mean for you, the listener, trying to deploy AI?
It means unparalleled flexibility and performance.
Right. It means you can deploy your AI models much more easily,
Yeah.
regardless of where they were originally trained or where they ultimately need to run. It's that bridge, getting AI from the lab to the real world.
Okay, let's zoom back in on one of those pillars we mentioned earlier, quantization. You called it a cornerstone technique.
It absolutely is. So reiterate for us, its core purpose is reducing numerical precision, right? Typically from 32-bit floating point down to simpler 8-bit integers.
Exactly. FP32 down to INT8 is the most common, but other bit widths are possible too.
And the benefits are huge, you said, like 4 times smaller models.
At least 4x reduction in size, yeah. And typically a 2 to 4 times reduction in memory bandwidth needed, which leads to a 2 to 4 times speed up in inference.
Wow.
Especially on specialized hardware that's optimized for integer math. It's almost like magic for resource-constrained environments like edge devices or even just reducing cloud costs.
So how does it work? How do you squeeze those detailed numbers into smaller ones accurately?
The core idea is a linear mapping. Basically, you define a scale factor, S, and a 0 point Z. The formula looks something like real value scalar quantized value 0 point. Don't worry too much about the exact math, but the key is that this mapping allows you to represent a range of floating point numbers using integers. And critically correctly representing the real value of 0 is crucial.
Why is 0 so important?
Because things like padding and convolutions, or the effects of ReLU activation functions, which output 0 for negative inputs, rely heavily on the exact value of 0. Getting it wrong can really mess up the math.
Ah, okay. So you need to map 0 perfectly.
Yeah.
What else affects the accuracy?
A few key things. First, Symmetric versus asymmetric quantization.
Okay.
Symmetric quantization forces the 0 point z to be 0. This is simpler, computationally cheaper, and often works well for distributions that are naturally centered around 0, like most model weights tend to be. Asymmetric allows the 0 point z to be something else, which gives more flexibility to accurately represent skewed distributions, like the outputs of a ReLU function, which are always 0 or positives.
You might use different types for different parts of the model.
Very common. Often symmetric for weights, asymmetric for activations. It gives the best balance.
Okay. What else?
Granularity. This is huge. Per tensor versus per channel quantization.
Granularity, meaning how finely you apply the quantization.
Exactly. With per tensor, you calculate one scale and 0 point for an entire tensor, like all the weights in a layer.
Sounds simple.
Simple, yes, but potentially disastrous. If the values within that tensor vary wildly, maybe most are small, but there are a few huge outliers, those outliers will dominate the calculation of the scale.
And crush the precision for the smaller values.
Precisely. It can kill accuracy, but with per-channel quantization, you compute separate scale and 0 point parameters for each individual channel, say along the output channel dimension of a convolutional layer's weight tensor.
So it adapts better to variations within the tensor.
Massively better. And here's where it gets really interesting, almost shocking sometimes. Think about well-known models like MobileNet V1 and V2.
Yeah, classic efficient models.
Right. If you apply naive per-tensor quantization to them, their accuracy can plummet catastrophically. We're talking near-random guessing, like 1.1% accuracy. Basically useless.
Wow, from highly accurate to useless, just from simple quantization.
With the naive per-tensor approach, yes. But if you apply per-channel quantization instead, the accuracy can be restored dramatically. For MobileNet V1, it could jump back up to over 70%.
That's incredible. Just changing the granularity makes that much difference.
It absolutely can. It shows how crucial these details are. Per channel is often essential for preserving accuracy in CNNs.
That MobileNet example really hits home. Okay, so not all quantization is created equal. How do we actually apply these methods in practice?
We generally talk about two main approaches. The first, and often the simplest to try, is post-training quantization, or PTQ.
Post-training, so after the model is already trained.
Exactly. You take your pre-trained FT32 model and convert it without any retraining. It's fast, inexpensive, often the first thing people attempt.
Makes sense. Are there different types of PTQ?
Yes. There's dynamic PTQ. Here, the weights are quantized offline beforehand, but the activations, the data flowing through the model during inference, are quantized on the fly.
On the fly, during the actual calculation.
Yeah. It doesn't require a separate calibration dataset, which is convenient. The main benefits are reduced model size and reduced memory bandwidth needed to load the weights. This is often good for models like LSTMs or RNNs, where weight access is the main bottleneck.
Okay, and the other types?
The other main type is static PTQ. This quantizes both weights and activations offline before inference.
How does it know how to quantize the activations if they change with the input?
Good question. It requires a calibration step. You feed a small representative data set, typically just 100 to 1,000 samples through the FP32 model. You basically record the range or distribution of activations at various points in the network. These statistics are then used to calculate fixed scale and 0-point values for the activations.
I see. So you use sample data to figure out the typical ranges.
Exactly. And because the scales and 0 points are fixed, it eliminates the runtime overhead of calculating them on the fly, which usually leads to faster inference compared to dynamic PTQ.
And for this calibration, are there different ways to calculate the scales and 0 points?
Yes, several advanced calibration methods. The simplest is just min-max, recording the minimum and maximum values seen. But this is highly sensitive to outliers. One outlier can wreck the range.
Right, like we discussed with per tensor.
Exactly. So better methods exist. Entropy, often using KL divergence, tries to minimize the information loss between the original FP32 distribution and the quantized one. This often gives the highest accuracy. Percentile uses a histogram and clips outliers, say at the 1st and 99th percentile, making it more robust than min-max. And mean squared error, MSE, tries to minimize the numerical difference between the FP32 and quantized values.
So you have choices depending on what you prioritize: robustness, pure accuracy, etc.
Precisely. You typically experiment to see which calibration method works best for your specific model and data.
Okay, PTQ sounds great for quick wins, potentially very effective with good calibration. But what if even the best static PTQ isn't accurate enough? What if accuracy is absolutely critical?
That's when you turn to Quantization-Aware training, or QAT.
Quantization-aware training. So
Yeah.
you make the training process itself aware of the quantization.
Exactly. QAT integrates the simulation of quantization effects directly into the training, or, more commonly, the fine-tuning loop.
How does that work? You don't actually train with 8-bit numbers, do you?
Not usually, no. The standard approach uses special fake quantization nodes, sometimes called QDQ nodes for quantize dequantize.
Fake quantization.
Yeah. In the forward pass of the training, these nodes take the FP32 weights or activations, simulate the process of quantizing them to INT8, calculating what the integer value would be, and then immediately dequantize them back to FP32.
So the computation stays in FP32, but the values have gone through a simulated quantization-dequantization step.
Correct. This introduces the noise and precision loss of quantization during training. The model becomes aware of this noise and learns to adjust its weights to be more robust to it.
That's clever. But wait, quantization involves rounding, correct?
Yeah.
How do you backpropagate gradients through a rounding operation which isn't differentiable?
Excellent point. That's the key challenge QAT had to overcome. The solution is an ingenious trick called the straight-through estimator, or STE.
Straight-through estimator.
Yeah. During the backward pass, backpropagation, when the gradient calculation hits the non-differentiable rounding part of the fake quantization, the STE simply pretends the derivative is 1. It just passes the gradient straight through as if the rounding wasn't there.
It just ignores the non-differentiability for the gradient.
Essentially, yes, it's mathematically unsound in a strict sense, but empirically it works incredibly well. It allows the gradients to flow back, enabling the model to learn weights that are resilient to quantization effects.
Wow, okay, that is a clever trick. And the benefit is higher accuracy.
Significantly higher accuracy, usually, especially when you're pushing to very low bit widths, like maybe INT4, or when dealing with model architectures that are particularly sensitive to quantization noise. QAT is often the gold standard for accuracy.
And what does the final QAT model look like? Is it actually INT8?
Modern QAT workflows typically output ONNX models in that quantize-dequantize QDQ format we mentioned.
The same fake quant nodes?
Yes. The model still has FP32 operations, but they are sandwiched between these quantilinear and dequantize linear nodes.
I keep them. Why not output a pure INT8 model?
Because this QDQ format acts as a clear signal to optimize backends like ONNX Runtime or NVIDIA's Tensoroid. They recognize this QDQ pattern, quantize dice FP32 up a dequantize, and know they can fuse this entire sequence into a single, highly optimized native integer kernel running directly on the hardware.
I see. So the QDQ format tells the runtime engine, hey, you can run this whole chunk using fast integer math.
Exactly. It provides the flexibility for the runtime to perform the best possible optimization. That's why QDQ is essentially the industry standard now for deploying high-performance quantized models trained with QAT.
This is really getting into the weeds of making things work efficiently. Let's push the envelope even further. You mentioned lower bit widths. What about sub-8-bit quantization, like 4-bit INT4?
Yes, that's a huge area of research and development right now, especially for large language models.
The compression benefits must be enormous. 8x smaller than FP32, right? And
Right.
2x smaller than INT8.
Exactly. Massive potential savings in memory and potentially speed, but there's a catch, a big one.
Always a catch. What is it this time?
The challenge we discussed earlier with outliers becomes much, much worse at lower bit widths like INT4.
Those few extremely large values.
Yes. With only 16 possible integer values in INT4, a single large outlier in a tensor can completely dominate the scale calculation. It forces the scale to be so large that almost all the other values get quantized to just 1 or 2 integer levels, often near 0.
So you lose almost all the information about the smaller, more numerous values.
Precisely. It destroys the precision. If you just apply the same naive PTQ techniques we used for INT8 directly to INT4, the accuracy often collapses completely.
So how do you solve that? You can't just ignore outliers.
The key innovation here is block quantization, also known as group-wise quantization.
Block quantization. Okay, sounds like the per-channel idea, but maybe more general.
Sort of, yeah. Instead of calculating one scale and 0 point for the whole tensor, or even per channel, you divide the tensor into much smaller contiguous blocks, maybe blocks of 32, 64, or 128 values. Then you calculate a separate scale and potentially a 0 point for each individual block.
So if there's an outlier, its impact is confined just to its own tiny block.
Exactly. It doesn't mess up the scaling for all the other values in the tensor. This preserves much, much more precision and information, making INT4 and even lower bit width actually viable. It's been absolutely critical for compressing large transformer models and LLMs.
That makes a lot of sense. Containing the damage, so to speak. And this leads us to something you mentioned that sounded really cutting edge. Q-Loray quantized low-rank adaptation.
Yes. Q-Loray is a fantastic example of combining multiple clever techniques, including block quantization, to achieve something remarkable.
What did it achieve?
Q-Loray made it possible to fine-tune massive LLMs, think 65 billion parameters on a single consumer-grade GPU with just 48 GB of VRAM.
Wait, seriously? A 65B model on one consumer GPU? That sounds impossible. It usually takes clusters of high-end server GPUs, right?
Exactly. Before Q-Loray, it was unthinkable. It really opened up fine-tuning large models to a much wider audience.
How on earth does it work? What's the magic?
It's a combination of innovations. The core idea builds on LoRa, low-rank adaptation. The massive base model weights are quantized down to 4-bit using that block quantization method we just discussed, and critically, they are kept frozen. They don't get updated during fine-tuning.
So most of the model is static 4-bit.
Right. The only parameters that are actually trained are a tiny fraction of additional weights called LoRa adapters. These adapters use the low-rank factorization principle, basically, representing the changes needed for fine-tuning with very few parameters. This drastically reduces the memory needed for the model weights, and especially for the optimizer states during training.
Okay, so frozen 4-bit base plus tiny trainable adapters. What else?
Q-Loray introduced a novel 4-bit data type called 4-bit normal float, or NF4.
Normal float. Why normal?
Because neural network weights often follow a roughly normal distribution, like a bell curve centered around 0. NF4 is designed to be information theoretically optimal for this kind of distribution. It uses quantile quantization.
Quantile quantization?
Yeah, it means the quantization levels aren't evenly spaced. Instead, NF4 assigns more representational precision, more integer levels, to the values around 0, where most weights actually lie, and less precision to the extreme outlier values. It puts the bits where they matter most for normal distribution.
That's really clever. Tailoring the data type to the data distribution.
It is. Then there's double quantization. This is another memory-saving trick. Remember those scale factors we talked about for block quantization? Each block needs its own scale, usually stored as a 32-bit float.
Right, so lots of small blocks means lots of scales to store.
Exactly. Double quantization quantizes the quantization constants themselves. For example, it might quantize the 32-bit float scales down to 8-bit floats. This further reduces the memory overhead, especially for the scales associated with the block quantization.
Quantizing the quantization parameters.
Yeah.
Meta-quantization.
You could call it that.
Yeah.
And finally, they used paged optimizers. This leverages unified Mali capabilities, intelligently paging parts of the optimizer state, which can be very large during training, between the limited GPU VRAM and the much larger CPU RAM as needed. This helps prevent those dreaded out-of-memory errors during fine-tuning.
Wow. So Q-Loray really is a symphony of techniques. Block quantization, a custom data type, double quantization, low-rank adaptation, and smart memory management.
Absolutely. It's not just one thing. It's about combining multiple innovations synergistically to smash through previous limitations. A real engineering feat.
It really shows how these compression techniques build on each other. So let's maybe take a step back and quickly revisit the other pillars, pruning, KD, LRF, specifically thinking about how they fit into these hybrid approaches.
Good idea, because in practice, you rarely use just one in isolation. So pruning, again, is about making networks leaner. We distinguish between structured pruning, removing whole channels, filters, attention heads, which is generally hardware-friendly, and often gives immediate speedups because the dense matrix structures are preserved, just smaller.
Okay, structured is good for speed.
Generally, yes. And unstructured pruning, which zeroes out individual weights, creating sparsity. This makes the model much smaller in terms of non-zero parameters, but often doesn't speed up inference unless you have specialized hardware or libraries that can efficiently compute with sparse matrices. Standard GPUs and CPUs prefer dense computations.
Right. Sparsity can be tricky for hardware.
And the process for pruning is usually iterative, remember? Train, prune a bit, fine-tune to recover accuracy, prune some more, fine-tune again, repeat until you hit your target size or speed.
Got it. Then knowledge distillation, KD.
Yeah.
The teacher-student thing.
Right. We mentioned response-based KD, where the student tries to match the teacher's output probabilities. logits. Using a temperature T1 in the softmax function for both teacher and student during training helps soften the probabilities and emphasizes that dark knowledge, the subtle relationships the teacher learned.
The teacher saying, it's definitely a cat, but it could be a lynx.
Exactly that kind of nuance. Alternatively, there's feature-based KD, where the student trying to mimic the internal activation maps or feature representations of the teacher at different layers. This forces the student to learn similar internal processing steps.
And Distilbert was a key example here.
Absolutely, a landmark. Distilbert used a clever combination: standard distillation loss on the outputs, but also a masked language modeling, MLM loss, like BERT uses for pre-training, and a cosine embedding loss to make the student's hidden states similar to the teacher's. This triple loss resulted in a model 60% faster, much smaller, yet retaining 97% of BERT's capability on standard benchmarks. A huge success for KD.
60% faster, 97% accuracy.
That's compelling.
And finally, low-rank factorization, LRF.
So LRF approximates a large weight matrix W, say, M by N, with two smaller matrices, UM by R and VAR by N, where R is the rank and is much smaller than M or N. The number of parameters drops from MEN to RAF M plus N, which can be a significant saving if R is small.
And you connected this to LoRa.
Yes, it's the same core mathematical principle. LRF can be used to directly compress a pre-trained model by replacing large matrices with their factorized versions. LoRa, on the other hand, uses it for parameter-efficient fine-tuning. In LoRa, the original large-weight matrix W is kept frozen, and you only train two new, small, low-rank matrices, often called A and B, whose product represents the update or change to W needed for the fine-tuning task. You add this low-rank update, B times A, to the output of the frozen W during inference. Same math, different application.
Okay, that clarifies the LoRa connection. So bringing it all together, what does it mean when you combine these? How do these hybrid strategies typically work?
It means the most powerful and effective compression strategies almost always involve combining multiple techniques in a well-thought-out, multi-stage pipeline.
A pipeline approach.
Exactly. A very common and effective one looks something like this. 1. You start with your pre-trained teacher model, your best performing but likely large and slow FP32 model. 2. You apply structured pruning to create a fundamentally smaller student architecture. You define the target size or sparsity here. Accuracy will definitely drop at this stage, maybe significantly.
Okay, prune first for size.
3. Now, you distill knowledge from the original large teacher model into this smaller pruned student. You retrain the student, but using the teacher's outputs, and maybe intermediate features, as a rich learning signal. This helps the smaller student recover a lot of the lost accuracy. Often, a distilled student outperforms a model of the same small size that was just trained from scratch on the original data.
So the distillation helps the smaller model punch above its weight.
Precisely. It transfers the wisdom of the larger model. 4. Finally, you take this pruned, distilled student model and apply quantization as the last step, either PTQ or QAT, depending on the final accuracy requirements to convert it into an efficient integer format for deployment.
Wow, that's a really logical flow. Pruning sets the capacity, distillation fills it with capability, and quantization optimizes the final representation.
You've got it. It's a principled engineering discipline for building efficient models.
Okay, let's put all this theory into practice with a final challenging example. A capstone project, if you will. Vision transformers, VITs. You mentioned they are powerful, but notoriously hard to quantize without losing a lot of accuracy. Why is that, and how would we rescue one using these techniques?
You're right, VITs can be tricky. The why often comes down to specific components within their architecture. Things like layer normalization, the softmax function, especially in the attention mechanism, and the GALU activation function tend to have activation distributions with very wide dynamic ranges or non-uniform shapes.
Meaning they have values spread way out.
Exactly, and those wide ranges are really hard to represent accurately with low-precision integers like INT8 using simple quantization schemes. The quantization just doesn't have enough bins to capture the distribution well, leading to significant errors and accuracy drops.
Okay, so they are inherently sensitive. How does the rescue mission begin?
Systematically. Step 1 is always benchmarking. Establish your FP32 baseline. What's its accuracy on your target task? What's its size? What's its latency on your target hardware? You need that starting point.
Measure first. Got it.
Step 2. Apply naive PTQ. Use a simple post-training quantization method, maybe min-max static PTQ. Measure the accuracy again. You'll likely see that significant drop we talked about. This quantifies the damage and confirms the sensitivity.
Okay, confirm the problem exists.
Step 3. Sensitivity analysis. This is crucial diagnosis. You use specialized debugging tools, often provided by the quantization frameworks, to pinpoint which specific layers or operations are introducing the most quantization error. Is it the attention outputs,
Yeah.
the MLP layers, the layer norm layers? You need to identify the culprits.
Find the troublemakers.
Exactly. Step 4. Mixed precision quantization. This is often the first real rescue strategy. Based on your sensitivity analysis, you exclude those identified highly sensitive layers from quantization. You leave them running in FP32 while quantizing the rest of the model to INT8.
So quantize everything except the few problem layers.
Right. This usually recovers a substantial amount of the lost accuracy. You trade a tiny bit of performance, because some layers are still FP32, for a potentially huge gain in accuracy, making the model usable again.
That seems like a practical trade-off. What if you need even more accuracy?
Then you move to step 5, targeted quantization-aware training, QAT. Instead of excluding the sensitive layers, you apply QAT specifically to them, or perhaps fine-tune the whole model with QAT. This allows those sensitive layers to adapt their weights to the quantization noise, typically yielding the highest possible accuracy for the quantized model.
So QAT is the ultimate accuracy recovery tool here.
Generally, yes. And as an optional, more advanced step, you could even integrate the earlier techniques. Imagine starting with pruning the VAT, then distilling knowledge from the original FP32 VAT into the prune student, and then applying the best quantization strategy, mixed precision or QAT, to that distilled student.
Layering the techniques for maximum effect.
Exactly. Building up the solution piece by piece.
And the final goal, after all this optimization.
The ultimate goal is to export your optimized, rescued model to that standard ONNX format. Now it's ready for deployment.
And you could deploy it anywhere ONNX Runtime works.
Pretty much. It could become a simple REST API web service running efficiently in the cloud, handling millions of image requests. Or, because it's now much smaller and faster, maybe it can run directly on an edge device like a Raspberry Pi, doing real-time image analysis right there.
From a sensitive giant to a lean, deployable model.
That's the objective. And the final satisfying step is always that comparison. Show the numbers. How does the final optimized model compare to the original FP32 baseline across accuracy, model size, and latency? That demonstrates the concrete value of applying these advanced compression techniques. It's a complete capstone-level success story.
What an incredible journey we've taken today, seriously. From understanding that AI efficiency gap, holding back these powerful models.
The deployment wall.
Right, the deployment wall, to mastering these really powerful techniques like quantization, pruning, knowledge distillation, and low-rank factorization, and seeing how they are just, isolated tricks.
They're building blocks.
Exactly. Building blocks for sophisticated multi-stage pipelines, culminating in the ability to rescue even really sensitive models like those vision transformers and make them truly practical.
And it's so important to reiterate, I think, that this knowledge isn't just theoretical, not just for research papers. It's fundamentally about making powerful AI truly accessible, scalable, and importantly, sustainable in the real world.
Sustainable is a great point, too, given the energy costs.
Absolutely. As models keep getting bigger and bigger, these techniques are what will actually unlock their full potential for everyone, democratizing advanced AI.
So a final thought for you, our listener, to maybe chew on as you go about your day. Given this explosive growth of AI models that we keep talking about, how might these model compression techniques truly shape the future of personalized AI? Could we see a future with powerful, custom-tailored intelligence running directly on your personal devices, your phone, your laptop, maybe even your glasses, without constantly relying on massive, energy-hungry cloud infrastructure? What would that enable?
It's an exciting possibility.
Definitely something to think about. Thank you so much for joining us on this deep dive today.
My pleasure.
We look forward to exploring more with you next time.